All right, so we have Joker today. He's going to talk about sphere version.
Okay. Well, first of all, thank you, Karina and Willie, for having me here. So I'm going to talk about something spooky today. So can everyone see the shared screen? Yeah. Okay, so what I'm going to do today is I'm going to take the sphere. I'm going to turn it inside out. But first, before we do that, we have to set up some background material. And it sort of relies on two ideological points I'd like to get across. So let's talk about the first ideological point. It's what is a smooth function? Really? So remember, from analysis, we learned what it means for a function to be smooth at a point. It means at that point, it has infinitely many derivatives. And that's an analytic condition, right? But now, recall even further back, before we even knew how to define derivatives and stuff, to calculus, where we sort of put this under the bus. If you're given a smooth function, called f, let's say it's smooth at the point 0, you can associate to it a purely formal object. Now, what is that object? It looks something like this. Okay. So remember, what is this? This is the Taylor series of f centered at 0. Oh man, okay. How do I make a new page? I'm just going to erase everything. Okay, so I just want to emphasize this object right here. That's purely formal. So it's just some collection of symbols, and they don't mean anything. And what I mean by that is this sum here is not a function, right? In order to check that it's a function, you need radius of convergence. You need to check that the series is well defined so that you can plug in values. So there's some work involved, but a priori, it's just a collection of symbols. Okay, so that's the first main ideological point. Taylor series and derivatives, collections of derivatives, are purely formal. I didn't know what a Taylor series was until last year, until I was talking with some first years. We were doing a problem about Taylor series. In the top right corner, it looks like there's a symbol to create a new page. Oh, okay, let's see. Oh yeah, thank you. Thank you, Tim. Great. Okay. So the point is we can view derivatives as purely formal objects, and we're going to treat them like that. So first, a basic definition from Top Geo 2. So if you haven't seen this before, be careful not to mess it up. So I'm going to define a vector bundle of rank k. This is a triple. So you have a smooth manifold E, smooth manifold B, and a map pi. So pi is smooth. Everything's smooth here. This is also surjective. And you want that for every point. And so, okay, sorry, let me give these guys names. This is the total space, and B is for base space. Okay, and you want that for every point B, little b in the base space, the inverse image of that point is a rank k, dimension k vector space. real vector space. That's not all. I require a bit more. I also require for every point little b in the base, there's a neighborhood, UB, and a diffeomorphism, where this is mapping from the preimage of the neighborhood to the neighborhood cross RK, such that this diagram commutes. Okay. And you also require that, maybe this follows from the definitions, but I don't think so, that if you restrict your phi sub UB to the fiber, this should induce a vector space isomorphism with RK. Okay. And these things have a name. These charts, U phi, these are called local trivializations. Okay. Okay, so, oops. The real meat of a vector bundle is in the data of the local trivializations. It sort of determines the vector bundle. And the local trivializations are there to say that locally, our bundle resembles a product. So here's what so if I have a local trivialization like this, then the bundle above it looks like a product. So this is UB, and this is UB cross RK. Okay. Okay. So now here's another definition. If you have a vector bundle, I'm going to define a section to be a map from the base space to the total space, such that inverse image, such that it's a right inverse to the projection. So S is a section. That's the definition. Now, what does a section look like on a local trivialization? This is the second ideological point I'd like to emphasize. So a section looks like the graph of a function from UB to the fiber RK. So sections locally resemble graphs of functions from the open set to the fiber. So sections look like graphs of functions, and the functions are from the domain to the fiber. Okay. So, I mean, my base space is a manifold, so I can pretend this is Rn, for example. So now we're going to study smooth functions from Rn to Rk. Okay. So here's a question. So let's study smooth functions from Rn to Rk. Here's a question. Well, let's do an example first. Let's look at a smooth function from R to R. How many derivatives of order up to order R does it have? So, a question to the audience. There are no tricks here. So, question was, how many derivatives does it have up to order R? And it's a smooth function. Everything's smooth. Tim?
Would that be R?
Ben Wu just said R. Yeah, so it's exactly R. Thank you. Right, you just take the Taylor. I mean, you just take the, here's one way. You can take the Taylor series and you just count the number of coefficients. Or you just take derivatives up to order R. Here's a harder question. No, I won't do a new page. Let's do the same question, but for a function from Rn to R. So same question. How many derivatives does it have? Up to order R. Well, let's do it for a given degree. So fix a degree R. So how many derivatives does it have of degree R? Well, this is, so a little counting is involved now. For example, if you're looking at R3 to R, let's say you want to look at degree 2. So you want to count all the partials of, you want to count all the second partials and all the different variables. So this is like if you have 3 boxes, X, Y, Z, and you have 2 balls. Those are the degrees. You need to put the balls into the boxes. So count the number of ways you can put the balls in the boxes. So for example, if you put both balls into X, that's XX. If you put 1 into X and 1 to Y, that's XY. Notice that's the same thing as putting 1 into Y and 1 into X. So this accounts for equality of mixed partials, and so on. So this is a combinatorics problem. You have to use stars and bars or something. I was never very good at that. So I'll just tell you the answer. So in degree R, the number of derivatives is, let's say D and R is, oh boy, n plus R minus 1, choose n minus 1. Okay, so it's quite annoying. So then the total number of derivatives up to order R would be, you have to just count all these D and Ks. So this is the total number of partials up to order R. Okay. And then, of course, we can do the same thing for function from Rn to Rk. It's the same formula, except now you have k components. So you have k times d and r in degree R. And then you have to sum up over R also if you want to count all the derivatives up to a given degree. Okay.
Wait, why do we have the k times d and r in this case?
Oh, because my function is a map from Rn to Rk. So there's k different functions from Rn to R. So then I just multiply.
Right.
Okay, so that was a bit of counting. That's probably the hardest thing we're going to do in this lecture. Let's see. So let's collect all this information into one definition. So suppose you have a smooth map, Rn to Rk, and you have a point in Rn. So this is the most important definition, I think. I'm going to define a tuple. I'm going to call it JR of F for point X. This is the tuple consisting of the value and all the derivatives. So let me explain the notation. So these are all the derivatives, all partials, in lexicographic order. So, for example, F, let's say if you have a map from R3 to R, then F prime at X is df at X, df of Y, df of Z, And f double prime is, you have to do this lexicographically, so I think it goes xx, xy, xz, and then it's yy, and so on. So I just compiled all the derivatives into one thing. I just collect all the derivatives into one thing and then consider it as a tuple. Okay. So let me draw a picture of what a one-jet looks like. So remember, if I have a function from R to R, I can look at its graph. And then J1 of f will look like, it will have the same graph as above, but with extra information, it's going to have the first derivatives recorded. So it's going to look like all these little tangent lines are there too. It's kind of bad because they're not, I can't draw tangent lines, but so the important thing is jets record derivatives. Now if I go back here, let me just go back here. So JR of f, so this is the value, oh man, f of x, f prime. So there's a reason I want to count derivatives with you guys. I hate counting. So this is, so f is again, f is a map from Rn to Rk. So this target here lives inside of Rk. This is the first derivative. So that sits inside of, so how many first derivatives are there? There's R, K, D, and 1, right? We have to count all the partials. And then all these, so all these guys live in Euclidean space like that. Okay. So let's come to the next big definition. So definition. The space, I'm going to write JR, Rn, Rk. This is Rn cross Rk cross R, K, Dn1. Oh boy. So R, K, Dnr. This is called the Rth jet space. Of maps, or the space of R jets. Of maps from Rn to Rk. And remember, if you have a function, it gives you a section. So, and vice versa locally. So this is also the space of R jets of sections of the bundle Rn cross Rk over Rn. Remember, a section of this bundle is like a map from Rn to, whoops, Rk, the fiber. Okay, so how do I think of this space? We think of this space as the space of all a priori formal derivatives. Right? If you have a function from Rn to Rk and you take its derivatives, if you take its Rjet, then that's a point in this space. But there are other points in here. They're like derivatives, but formally. So, okay, so for example, let me do an example. Let's look at J1 Rn cross Rk. So this is going to be Rn cross Rk, and then it's going to be all first derivatives. So we sort of know what that is, right? If you have a multivariable function, its derivative is a linear map. This is m k by n. So remember, this is the same thing as Rkn. where this is the space of all k by n matrices. So like I'm considering all possible values that a function could take and all possible derivatives a function could take. That's my jet space. Are there any questions so far?
Tobias,
Yeah.
why are they called jets?
Oh yeah, I was thinking about this. I think it's like a Taylor polynomial is like if you take a spray bottle or something and you spray it, like jets out. That's as best as I got. I don't know why they're called jets. I have no idea. I should say also that if you have just a general, so this is for the senior students in the audience. If you have a general fibration or more general type of bundle, then jet spaces are defined for those also. So you have JR of X. Okay. And I didn't say this, but notice in our case, oh yeah, so, okay. Sorry, I'm jumping ahead of myself. So jet spacers are defined for general fibrations, general bundles, but locally they'll always look like what we've been discussing so far. Locally they look like products of Euclidean space. So they're finite dimensional manifolds. It's pretty good. Also, notice this guy. I mean, this is a product, right? It's Rn cross Rk cross some crap. This is a bundle over Rn cross Rk. It's also a bundle over Rn. So this is a bundle. This pairs and this map in between is a bundle. And this is a bundle. And also this composition is a bundle. So we've sort of collected all possible derivatives into bundle theory. So we're going to study derivatives using topology and geometry. So that brings us to the next section. This is going to piss off Liz. She's in the audience. What is a PDE really? Okay. So the point is, equations are also purely formal. It's kind of weird. Algebra is a human mental construct. It's purely formal. And so we can study them. So we can study them using these formal derivatives. So let me give a definition. So an rth order PDE or PDR, so partial differential relation, let me do PDE in parentheses actually, is a closed subspace of JR. So a PDR, partial differential relation, is just a subspace of your jet space, your jet bundle, and a PDE is one that's closed, right? It's described by an equation equals 0. That's a closed condition. And a PDR can have inequalities. So for example, let's look at this relation. This is a subspace of J1 Rn Rk. Oh yeah, usually also these PDRs usually tend to be subbundles also, so that's pretty nice. They don't have to be, I don't think. So this relation, it's going to consist of all jets. So this is, remember, this is the domain, this is the target, and this is the derivative. It's the formal derivative. This consists of all tuples such that L is, oh, let's say n is less than k. L is injective. So this is called the immersion relation. So why am I setting things up like this? So let's say you have some jet bundle. And let's say you have a section down here, call it S. Then there's a natural way of obtaining a section on top. You just take the rth jet. You just take derivatives of the function given by the section. So let me write this out, S of x. So I'm taking derivatives of the function f from Rn to Rk. So I'm not taking derivatives of sections. I don't need a connection or anything like that. And then Jr of s is just the derivatives of the function. Okay. And we remember what that looks like. You know, sections locally look like graphs. It's got all this tangent information. However, notice you can have a section up here. Now, the question is, does it come as a section down here? And that's not always the case, right? Because suppose you have a section upstairs. That means it locally looks like this, but you could have formal derivatives. So it's not necessarily actually tangent to the function. Right? The data of a section from Rn to Jr is you need a target point, and then you need some collection of derivatives. But the derivatives don't have to be the derivatives of the actual function. So it looks like, so an arbitrary section of Jr looks like the right-hand side, and sections that are actually derivatives of functions look like the left-hand side. There's a name for these guys. Let's call a section that does come from the derivatives of the function holonomic. And actually, I don't have a name for this guy. So forget this guy. Forget name. Okay, so we're really interested in holonomic sections because those actually correspond to functions. And the whole reason we study partial differential relations as subsets or subbundles so here's why. So here's another definition. Suppose you have a section from Rn into Jr that has image inside of the relation. So a section with image inside of the relation is called a formal solution of the relation. So it has formal derivatives, and those formal derivatives satisfy a formal equation formally. Everything's formal. And then if you have an actual section, so an actual function to Rk, whose derivatives live in R, so if you have a section that's holonomic, this is a genuine solution. Because then you actually have a function whose actual derivatives satisfy whatever algebraic equation you put. So, for example, if we go back to the immersion relation, a genuine solution of this relation are actual immersions from Rn to Rk. They're actual functions whose derivatives are injective. And it's less. This is great because that means we now have this formalism set up to study PDEs and PDRs topologically and geometrically. There's spaces. Let me give a small historical note. Okay, well, before I do that, let me give the actual definition. So a relation inside of some jet space, some jet bundle, satisfies the H principle if every formal solution is homotopic to a genuine solution. Meaning every formal solution, every section into JR with image inside of R, you can homotope it, possibly along sections, to a new section, which does come from the derivatives of an actual function. So this is like saying, if you have some relation that satisfies H principle, that's like saying you could solve your PDE completely using homotopy theory without doing any analysis. Let me give a historical note of interest, actually. So Tony Phillips, good old Tony, he used to work here. He's retired now. He was a graduate student of Milner, and Milner asked him something like, if you're given a surjective bundle map, when is it a submersion? And so he answered this question in his thesis, and he went to Russia, and then he talked to Gromov, and he told him this idea. Gromov's mind exploded. And then Gromov came up with, he generalized Tony Phillips' thesis to this thing called the H principle. And he started studying derivatives formally and attacking PDEs purely topologically. Okay. So I should say right off the bat, the H principle is not that useful. It's like people in PDE would not use it at all. And it's not very helpful for PDEs that arise in PDEs. It's not helpful for PDEs that PDE people are actually interested in. It's more useful for equations or relations that come up in geometry, like the Immersion Relation. Oh God, how did I screw that up? The Immersion Relation. Okay. So, you know, it's kind of amazing to even have a relation that satisfies the H principle. Like, how do you, right? That means you could solve it purely topologically. How do we even check a relation satisfies it? There's a lot of techniques available. Gromov does a bunch, introduces a number of techniques in his book, Partial Differential Relations. I'll discuss here one particular theorem. And then as an application, I will invert the sphere. I should also say Kevin Sackle, he's a postdoc here, also specializes in H principle. He knows a lot. Okay. So before I state the theorem, I'm going to give you a guiding picture. You have the plane. You have a compact interval in there. And let's say you have a little open set. And let's look at let's look at J1 of R2 to R. I have a formal section. I have just a formal, I just have a section. And it's going to be defined as f of xy is, here's the domain point, here's the target point, x, and then the derivatives are just flat. So what does this look like? This looks like a line, and it has flat derivatives. So you have all these planes here. So obviously the planes are not the derivatives of the function. They're like, you have some line and you have some flat planes. So the question, maybe for you hikers out there, how do you climb a very steep mountain on a flat path?
Take stairs.
Yeah, it's close enough. I was thinking you could do this. You could sort of wind around like that. Right, go all the way across, go all the way back, all the way across, all the way back. So this section that I just drew, this red wiggly line, has almost flat derivatives, but it's not defined on this compact interval down there. It's rather defined on a wiggled version of that compact interval. So the following theorem will say, if you're given a formal solution, any section of the jet space, you can approximate it in a C0 sense by a holonomic section, given that you can perturb the domain and the actual target in the jet space. So you have to wiggle on top and you have to wiggle on bottom. So here's the theorem. It's called holonomic approximation. So it says, take a submanifold of positive codimension. Oh God, okay. So I'm gonna let U A be a neighborhood of A. Anytime I write U sub anything, it's gonna denote a neighborhood of that anything. Fix a metric on the jet space. And suppose you have some section, some formal section. Then, for any delta and epsilon, there exists a C0 delta small diffeotopy. So that's a homotopy along diffeomorphisms. And a holonomic section on a neighborhood of the image of the last guy in the diffeotopy, such that these guys are very close together. And the neighborhood of the image of the diffeotopy is very small. It's going to be contained inside of the neighborhood of A. So you can actually compare these values here. Right, X is inside of UH1 of A, and that's also going to be considered. It's also going to be contained inside of U of A. Okay. So, yeah, this is quite a technical statement, but the idea is literally, so if you go back to this picture, the compact interval is my A. The wiggle downstairs is, the image of that is my H1 of A. And there's a small neighborhood around it that's contained inside this big neighborhood. And then this section right here is my holonomic section. So I can approximate any formal section by wiggling the base. And the point is, the positive codimension gives me literally enough wiggle room. And notice this approximation is only C0. I mean, I don't have to tell the analyst twice here. It's like approximate, it's like saying, it's like the proof that square root of 2 is equal to 2, right? I can make the wiggles, I can wiggle as much as I want, and it will be very close, but the derivatives are getting very big. Okay. Okay. And I should also say this theorem, you can apply it for families of sections. So it holds parametrically. You put T's everywhere. And the family is sort of glued together so everything works out. Okay.
Sorry, I don't understand. Could you say one more time what C0? What is C0?
Oh yeah. So if you look at this top picture, F with the planes, these flat planes, that's black F, and then I have this wiggled F tilde here. These guys are C0 close. So the underlying functions are very close. So let me draw a better picture maybe.
Okay, got it, thanks.
Yeah, so it could be something like this.
You said that the derivatives become very large, but in the statement of this lemma, haven't you said that the values of f and f tilde are still very close to each other?
Right. So they are still close in the jet space, but then you have to, once you pull everything back to a common domain, then you lose derivatives.
Okay.
Yeah. So once you pull everything back to a common domain, because right now the C0 approximation is defined on, I'm comparing them on, so suppose that's my A, and then I have this new wiggle. I'm comparing the functions on the neighborhood of this wiggle. So if I pull everything back to A, then the derivatives explode. Okay. Any other questions? We're going to use this to turn the sphere inside out. Let's use this theorem. So, sphere inversion. I'm going to fix delta, and I'm going to take V to be the thickened sphere. So, it's all the XYZ such that it's between these two guys. Right, it's the two sphere, and then I made the shell a little thicker. It's called I and V, the inversion map. This just takes a point and sends it to its inverse. And then I need this extra map actually. So this is reflection along the z-axis. So, okay, so I write big, so it's kind of annoying. But okay, so remember these remember these maps. You have inversion and R for reflection along the z-axis. And then I'm just going to write I big V to be the inclusion. And then here's the theorem of Smale. You look at the maps, R composed with I and V, composed with the inclusion. And you look at the map, the inclusion. So these are not only homotopic, but they're homotopic along immersions. So that's what it means to turn it inside out, that they're the inclusion is homotopic along immersions to the inverse. So notice, if I just have inv with the inclusion, this also turns the sphere inside out, but it induces the wrong orientation. That's why I need the R. So it's not homotopic. So here's the statement of the theorem. Okay. let's prove this thing. Okay, so proof. We're going to do the holonomic approximation theorem, which says given some section of the jet space, I can wiggle the bottom and get a holonomic section, get an actual section that comes from derivatives. That's why I need to thicken the sphere, because I need positive codimension. I need enough wiggle room. So let's see. So let F0 be the inclusion, F1 be my map of interest. So both of these guys are immersions, have rank 3. So these are maps from, whoops, V to R3, and induce the same orientation. So you can think of these as sections of J1 V R3. So you have 0 and you have F1. So, and remember, this is V cross R3 cross M 3 by 3. Now, they're both full rank and they both induce the same orientation. So I can do even better. They're maps into SO3. So you can, so these are sections. So you can think of these as maps from V into R3 cross SO3, right? Sections give you functions locally, and locally because locally they look like graphs of functions. Okay, so now you have these two maps, V to SO3. Now cross R3. Now V is a thickened sphere, so this is homotopic to S2, and this is homotopic to SO3. I only know 3 things about Lie groups. Pi1 is abelian, and that's true for any topological group. And Pi2 of any Lie group is 0. So Pi2 of SO3 is 0. And the third thing is, if you have a Lie group where Pi1, Pi2, Pi3 all vanish, then it's actually a Lie group isomorphic to Euclidean space. But okay, that's, I mean, that's a little going off track. So you have Pi2 SO3 0. So these two derivatives are homotopic abstractly. So remember, so these two derivatives, and they're homotopic upstairs. But we want this homotopy to come from derivatives of actual functions. We want the homotopy itself to be holonomic. So now we're going to apply holonomic approximation to the homotopy. So take A to be S2 and apply holonomic approximation. That's the wiggling theorem to each FT. And we can do it parametrically. So this gives us a family of holonomic maps. But they're all defined on different like neighborhoods, which is kind of annoying. So these neighborhoods are all neighborhoods of perturbed spheres. They're like the neighborhoods of H. I wrote H1, S2, but there's a different H1 for each T. So you have all these different perturbed spheres and all these different neighborhoods. But all these neighborhoods are small, and there's a natural contraction map from V into UT. So then this composition, so this is my FT tilde, this composition is going to be my GT. And for epsilon very small, each of these FT tildes are going to be immersions also, because immersion, being an immersion is an open condition. So then these GTs, so then GT is a homotopy of immersions between F0 and F1. Kind of a letdown. It's kind of hard to see exactly what this eversion process is in this proof because it's not explicit, because we just used that pi2 of SO3 was 0, and then we used the H principle theorem to wiggle and approximate it. But yeah, so this is not the, I'll just say a few concluding remarks. This is not the proof or construction that's on that famous YouTube video where you turn the sphere inside out. That was Thurston's corrugations. That's a different method. And it's a lot easier to invert the sphere using other techniques than having to go through this H principle business. Okay, so I'm gonna stop there. It's good time to stop.
All right. Thanks very much, Joker. Any questions?
I have a question. Can you do it for higher dimensions also? Like, is it something special about dimension 3?
Oh,
or?
everting the sphere? So I think it's, no, I don't think so. So there's a, right, I think it's a theorem that the only spheres you can invert are S2 and S0, and maybe S6. Yeah, but I have no idea how that's proven. Thanks for coming.
Could I ask a question?
Yeah.
Is there like a infinity jet space?
Yes. So
there should be.
Yeah. So there's J1. All these J's are bundles over each other. Oh yeah. Oh, right. I should say, in the local case, they're vector bundles, but in the general case, they're just affine bundles. There's no vector space structure. But eventually, if you take the inverse limit, there's a J infinity.
Right.
This is like infinite dimensional manifold. It's not nice.
Do you know if people study this thing, or is it?
Yeah, there's a whole like industry of people. I don't know if you, so last year, maybe 2 years ago, there was a postdoc here, Ben McMillan. He was a student of Duke. He was a student of Robert Bryant at Duke. Mm-hmm. And there's like a bunch of these exterior differential systems people that study J infinity.
Cool, thanks.
Any other questions? All right. If not, let's thank the speaker again. Thanks very much.
Happy Halloween, guys.
Happy Halloween.
Great talk, Tobias. Thank you.
Thank you.
Take care.
See ya.
All right. See you guys.